All right, everyone. Welcome to another episode of the TWiML AI podcast. I am your host, Sam Charrington. Today, I'm joined by Markus Nagel. Markus is a research scientist at Qualcomm AI Research. Before we get going, be sure to take a moment to hit that subscribe button wherever you're listening to today's show. Markus, welcome to the podcast.
Thanks a lot, Sam. I'm happy to be here.
I'm looking forward to digging into our conversation. We'll be talking about some of your recent research that you're presenting at NeurIPS, as well as some of the other Qualcomm research that appeared at NeurIPS. Before we dig into those papers, though, I'd love to have you share a little bit about your background.
Yeah, sounds good. So kind of my background and how I got into AI started with doing an undergrad in computer science in Germany. And like during my degree on computer science, I was always interested in data-driven algorithms, especially like topics like computer vision, pattern recognition, and things like that. So for my bachelor's thesis, I actually did a very interesting internship at CERN. There at CERN, that's where the Large Hadron Collider is, and there I did a project on pattern recognition for beam loss monitoring. So that was kind of my first real ML kind of driven project. And after that, I was still excited about the topics, and that brought me to Amsterdam. And in Amsterdam, I followed a degree, a master's degree in artificial intelligence at the University of Amsterdam. And of course, we studied a lot of interesting topics there, like machine learning, reinforcement learning, computer vision, natural language processing. And then like I went more and more towards the research side. Also in my master thesis, I worked on some more computer vision related topic. It was called event Fisher vectors. So it was encoding of diverse visual streams of photos, for example. And we also submitted that one then later to a conference, first to CVPR, where unfortunately I had my first rejection as a researcher, but that's common.
Important milestone.
It's an important milestone and very common in the field. And then later we resubmitted it and it got accepted at BMVC.
And what's the focus of your research nowadays?
So now I'm at Qualcomm AI Research, and actually, I had an interesting journey there. And to become a real researcher at Qualcomm AI Research so I was always after my master's between doing a PhD or going to industry. And actually, it brought me to a third option, which is a startup called Cypher. That's a startup from Professor Max Welling, which you probably know, and also like Taco Cohen and Twyman Blanquefort, who have been earlier on your podcasts like a couple of years back, I think. They were co-founders of that startup. And that is sort of what, in the end, brought me to Qualcomm. So we did a lot of interesting machine learning problems there, a little bit more on the applied side. But then in 2017, Cypher got acquired by Qualcomm, and that kind of brought me back into doing more academic research and working on less applied projects.
Wow, it's hard to believe it's been 6 years already.
Time flies indeed.
And so what are your current research interests?
My current research interests focus in general on efficiency of machine learning, and specifically I'm focusing mainly on inference efficiency. So how can we make machine learning models as efficient as possible? And some of the techniques for that is quantization, pruning. There are also knowledge distillation and other techniques in the fields to make inference as efficient as possible.
I guess that brings us right to the first couple of papers that we want to talk about today. These are papers that you're a co-author of, and just a couple of the papers that Qualcomm authors have at this year's NeurIPS. What I found interesting about the first one that we want to talk to is that I've had many conversations with Qualcomm researchers over the years about quantization and how, we've been improving quantization methods. And more broadly in the field, transformers are kind of taking over lots of different modalities, and this first paper is applying the quantization research to transformers. The paper specifically is Improved Transformers Quantizability by Getting Rid of the Outliers. So let's dig into that one. Talk about the problem that you observed with regards to outliers and quantizability for transformers.
Yeah, sounds great. Yeah, it's indeed very interesting research. And actually, sort of in the title of our paper, we have 3 different components. So the full title is Quantizable Transformers, Removing Outliers by Helping Attention Heads Do Nothing. And kind of the first part of the title, Quantizable Transformers, basically is our motivation. So we want to make transformers easy to quantize because historically they are not very easy to quantize, especially the activations. And that's sort of what the second part is about removing outliers. The outliers is really what is the problem in quantization of transformers. As there are in all types of transformers, there's many outliers, and these outliers are the problem because we have the typical trade-off in quantization between the clipping error and the rounding error. So it's this range versus precision trade-off. And if we have a lot of outliers while the main part of the distribution is fairly well behaving, then we can't represent both of them well. And that is what in the end can break quantization, and specifically in transformers, the activation quantization. And the third part basically of the title says attention heads doing nothing. And this is actually related to a very interesting finding we had. And that is actually that the root cause of the outliers comes actually from attention heads wanting to do a no update behavior.
Mm-hmm, mm-hmm. Was the impact of outliers and the disruption that it was causing from a quantization perspective, was this a known problem, or was this something that was discovered as part of the research?
No, that was really a known problem. So that is already known since we had in 21 already a EM-NLP paper on that topic, and there's also many other works which recognizes them. What is the main difference between our work compared to prior work is that most prior work is really trying to work around these outliers. So it's, for example, saying I don't quantize some outliers and keep a few of them in floating point, or it's, for example, saying certain type of activations where the type, like for example, after the residual addition, there are a lot of outliers. Then some work keeps these activations in floating point. But this is more really like a workaround, but they're not really tackling and analyzing what is the root cause of these outliers.
Mm-hmm. Okay, and so again, in your case, you found that to be the behavior revolving around the attention heads. How did you identify that as the kind of the root cause?
Yeah, so we looked into really the behavior of the outliers. So we did a lot of studies on where do they occur and when do they occur, and some interesting patterns we found, and some of these patterns were also known before, is that these outliers, they are only in very specific channels. And if I look over multiple layers, so multiple attention blocks, they're usually in the similar or same channels across multiple blocks. And also they're always associated to very specific tokens. So if you're talking about language transformers, then it's often some type of delimiter tokens. So for example, can be the separator token in case we have them in our embeddings, otherwise some punctuations like dots and commas. And if you're talking about vision transformers, we also show these kind of tokens are usually background tokens. So, and we found it very interesting. We were wondering what are encoded in these kind of meaningless tokens almost, because they don't have much information, a background token or a comma or dot. And we were wondering what actually happens there, and that kind of brought us digging really deep into what's happening inside the attention head. And what we found is that the outliers, they're actually associated that like other tokens put all their attention to these non-meaningful tokens. So basically it means like instead of, if I don't want to do anything, I'm not attending randomly to all tokens, but I'm only attending to these special tokens. And what we then see in the value matrix, so in attention, right, we have the attention weights, which gets multiplied then by the values. And what we noticed is that the values of these special tokens, they're often 0 or extremely close to 0. So what it actually means is like our outliers correlate to attending to tokens which have in the value zeros, and then like multiplying these two things obviously leads to a 0 output, and then like to no update on the hidden representation.
So it wasn't just the delimiters; it was that the delimiters were creating relationships with other low information tokens, and that was causing the problem.
Yeah, exactly. It's more like if a token. So, for example, think about we have a sequence, and we have like multiple layers, like usually like often like 20, 30 or more blocks in LLM. And then we slowly aggregate information and refine it. And at some point, especially towards the end of the LLM, it could be that for certain tokens, we just don't want to do an update anymore because probably the representation is good enough or is where it wants to be.
Yeah.
And then in attention, there's not any mechanism to easily say, I'm good, I don't want to update it anymore. And that's why we hypothesize it tries to attend to other tokens which have no information because their values are zeros. And then basically if it attends to them, it can achieve that no update behavior, which otherwise there's not a different way to do that.
So then what you do in this paper is create an explicit no update behavior, correct?
Exactly, or almost correct. So that's what we're trying to add to the attention head in our method. So for that, we introduce two methods, which are fairly simple. So basically, to do a no update, it means I want to be able to achieve exact zeros or exact ones to do a no update without having outliers. Maybe it's good to explain before shortly how the outliers relate to the no updates. So we established now basically that we want to do a no update behavior, and that can be done by attending to tokens which have no information. But then in order to get actually only attending to these tokens and not attending to anything else, we basically need to have in the attention weights, where we have the softmax, we need to achieve exact zeros and potentially exact ones if we only want to attend to a single no information token. But in order that the output of the softmax is 0 or very close to 0, we need to have a very big dynamic range in the input because they are relatively related to each other. And in order to have actually at the attention high dynamic range, there's one thing or two things which amplify that. To get that is normally there's always layer normalization between either on the residual or right before attention. And layer normalization is dampening significantly the dynamic range. But then to still have a high dynamic range, it means that the outliers in the layer before need to be even bigger in order to achieve these exact zeros. And also another kind of complicating fact is that softmax will never give exact zeros, which also means during training, we will always have a gradient signal, which then if we want to achieve that exact zero, basically always tells the layer before, make these outliers bigger and bigger and bigger. And that's basically exactly the behavior we want to counteract, and we want to slightly change attention to easily represent these exact zeros. We introduced two methods for doing so. One we call clipped softmax. So that's actually a fairly simple method. What we are doing is we take a vanilla softmax, then we slightly stretch the output of the softmax so that it goes from, let's say, minus 0.01 to plus 1.01, and then we are clipping it back to be between 0 and 1. So what that actually means is then with a finite dynamic range in the input side, this changed version of softmax can actually achieve exact zeros and exact ones during inference and also during training. And like that we can then say we don't want to attend to any of the tokens or only to some tokens with no information.
And the other method?
Yeah, exactly. So the other methods we call gated attention. So that's more explicitly modeling this behavior of representing exact zeros, because some of our early studies also showed that actually having the exact zeros is the main important thing and not the exact ones. So we model that behavior explicitly by adding one gate to the attention mechanism, and that basically can modulate the attention weights by just one row in the attention matrix. So that's the same dimension where we take the softmax over. We can modulate with a sigmoid gate. So it basically means we can, with a single parameter or with a single output neuron, we can say, oh yeah, here we don't want to have attention, and put that completely to zero.
And did those two methods perform equally, or did one turn out to be better than the other in some situations?
Yeah, they in most cases perform equally, but not in all cases. I think first the most interesting fact is that both of the methods, if we train a floating point model, they basically lead to the same performance in floating point domain as the original model, sometimes even slightly better, but not much. But then what we really saw is the resulting model has significantly less outliers. So in the paper we show that by measuring the maximum infinity norm and the average kurtosis. And of course, as a result, if we don't have these outliers, then out-of-the-box quantization is significantly better and works well. And comparing these two methods, in some cases they were almost the same, or clipped softmax was, for example, for the BERT model we evaluated slightly better. But we had one case, and that was on the OPT model, so that's a language decoder only model. We had, for some reason, that the clipped softmax didn't achieve the desired outcome, so there it kind of failed. So in that sense, but for all the other models like BERT and with clipped softmax worked well. So in that sense, yeah, gated attention seemed to work better in all three models we tested it on.
And how did you ultimately measure the performance of this approach relative to other kind of the traditional approaches to quantization, and how much performance does this kind of get you back relative to the original model that you're using in floating point?
Yeah, that's a very good question. So in general, we did not necessarily compare it directly to other quantization methods, because actually we placed this paper more not really as a quantization paper. So in a sense, this is not really a quantization method, but this is rather analyzing and getting rid of the root cause what makes quantization difficult, at least activation quantization. So in that sense, this work is completely orthogonal to any quantization method. So for example, we just do 8-bit post-training quantization afterwards to show that the model is easily quantizable. But if you want to get the best performance out, you could use any modern PTQ or QAT algorithm to apply on top of that. For example, GPTQ or other algorithms out here.
Right, because all the quantization methods suffered the same problems with outliers, and this is addressing that core root problem.
Exactly, like all quantization methods that want to do activation quantization.
You want it, right. But you still want to try to characterize the benefit that this approach offers. How did you do that?
So we did that. We applied post-training quantization with 8-bit activations to both the original model with the vanilla attention, so softmax-based attention, and then we compared the quantization performance of that one with exactly the same algorithms used to the performance we get when we train the transformer using the clipped softmax or gated attention.
And what did you find there?
We found there that both of our methods were significantly better. So for example, for BERT, even like the performance is close to random if in 8-bit activations, if you quantize really every layer and all activations. And with our methods, we have close to floating point accuracy.
Okay. Awesome. The second paper that you worked on that we wanted to dig into looks at pruning versus quantization. Talk a little bit about the context there.
Yeah. So the context here is that for model efficiency, so maybe first to one thing to mention and to distinguish it like in the mental switch from the other work is like the other work really was tackling activation quantization issues, and now we are looking in more general model efficiency and specific into the problem of weight compression. And for weight compression, to make the model smaller, there are two common techniques, either pruning or sparsity or quantization. And we really wanted to look at which of the two is better, because like both of them are fairly well-studied fields, also academically as well as from a hardware perspective, but it's very rarely that they are on a very rigorous manner get compared. And what we wanted to do in this work is to compare them as fairly as possible to draw conclusions what is better from an accuracy perspective.
Okay. And so tell us about how you approached this problem and what you found.
Yeah, so in order to make a fair comparison, we made a couple of assumptions, some base assumption. We compare in this study like uniform symmetric quantization compared to unstructured magnitude pruning. And we assume that the base data type is floating point 16. So it means we assume an equal compression rate if we have like 50% sparsity versus int 8 or 75% sparsity versus int 4. And that's sort of the base assumption of all the studies. And it's also a very common assumption that people assume FP16 is working without loss in accuracy. And then basically from there we compared like pruning versus quantization on various levels. So we started from comparing it on distributions to characterize how the error is. Then we looked at real weight tensors. And then we went to what happens if we add, for example, post-training pruning or post-training quantization algorithms on a layer by layer basis. And finally, we had a set of comparisons with end-to-end model fine-tuning.
And what did these comparisons show you?
Yeah, so basically these comparisons show that overall quantization is significantly better in most cases than pruning. So what we really can see is that in many of the cases it is better, and there we only found a few cases in which pruning can be better in quantization. So for example, one interesting study we did is we took all the weights from PyTorch model Zoo, as well as like the weights from several LLMs from Hugging Face, and we quantized them to a lot of different bit widths and the corresponding sparsity ratios. And then we looked at them, where is the SNR better for pruning or for quantization. And we noted that only in very specific cases, that's mainly low bit widths, and then also cases where we have many outliers in the weights. In these cases, pruning can perform better. So we can see that when we look at the kurtosis. So we kind of transform the data to plot it as a function of the kurtosis, and then we could really see if the kurtosis is high, which indicates there are many outliers in the distribution. Then it can be that in the 2-3-bit scenario, which corresponds to 85 to 90% sparsity, that in these cases pruning can perform better.
Mm-hmm. And so how consumable is this result for folks that are trying to create smaller models? Is this saying, just go straight to quantization and don't worry about pruning unless you're doing model A, B, and C? Or do you still need to kind of look at both for your particular use case because it's very use case dependent?
It's not very use case dependent, but one may ask, okay, what happens if we add algorithm to it? Like, for example, if we optimize it with modern post-training quantization algorithms or pruning algorithms. And actually, that was a big part of our work to answer that question. And in order to answer that question, we were deriving upper bounds on the signal-to-noise ratio for pruning and for quantization. And then actually we read it on part of the data, the same study, but with this upper bound, which tells us basically it doesn't matter what algorithm will be invented in the future, the SNR will never be better than that. And then we basically compared on many of the weight tensor the data for that, and sort of the findings were fairly similar to what I mentioned earlier on the real weight tensor, but this is a really good insight which kind of shows that at least for post-training quantization or pruning algorithms that we can like have much stronger guarantees than just looking at some random data or one specific algorithm.
Again, though, from a user perspective, if you're only looking at upper bounds and not also providing lower bounds, I still kind of need to look at both approaches in order to know what's going to be best for my specific data and algorithm, right? Or no?
Not necessarily specific. So we have a lower, I mean, the lower bound is the algorithm we have. So that's a very standard algorithm, like, for example, Algebra for quantization and a similar data optimized algorithm for pruning. So that's our lower bound. And we show in the paper, we make a nice plot with some squares, basically where one weight tensor is represented by one square. So the lower left corner indicates there what's the SNR for the two achieved algorithms, and then basically we span a box which kind of goes in the X and Y directions, what is the bound, and basically we know if that bound will intersect the diagonal of that SNR plot, then we know it may depend on the instance of the algorithm, and in the cases it is above or below the diagonal, it says that it's independent of the algorithm, either pruning or quantization would be better. Depends where the box lies.
Okay. Great. So we also wanted to talk through some of the other papers written by your colleagues there at Qualcomm. Why don't you walk us through, I think we've got 4, walk us through the ones that you think are most interesting there.
Yeah, sounds good. So the third paper, or the first of the other papers I want to talk about, is also a paper from the model efficiency team where I'm working in. It's called Scalarization for multitask and multidomain at scale. And that one really looks in more the training side. So what happens if we do training with multi-domain and multitask? Because like this kind of training with multi-domain learning and multitask learning, that can be also seen as a way of compressing information into one backbone. And there can also be knowledge transfer between the different tasks or different domains, and that can also improve efficiency. So that's kind of why we're looking into that.
The idea here is that, or is the idea here that we're able to take advantage of unique properties of multitask and multi-domain learning to make training more efficient? Yeah,
it can both make training more efficient, but it can also make inference more efficient, because if we train a model with multiple tasks, that means the model can do these multiple tasks at the same time, instead of running like 3 independent models for inference at the same time. So it tackles both efficiencies. And the specific work looks into how to do these multitask and multi-domain learning in the best manner. So a very common baseline for it is scalarization. So it basically means we have these multiple losses for the either multiple tasks or multiple domains, and then they're like summed together for the final loss with scalars. And prior work either uses just uniform weighting of the different losses, or sometimes statically tune them. And also there's sometimes some automatic adaptation of the scaled loss based on, for example, gradient information. And we're kind of like, or like my colleagues, are taking a slightly different approach, which basically can adapt the scalar weights of the different losses during training. So what they introduce is population-based training, and that basically means that with population-based training, we tune these scalarization weights of the different losses. And how you can think about it is that it's a kind of typical evolutionary algorithm which tune these weights, and we have a population of models. So basically we then, like at every step, we train like n models at the same time, but n doesn't need to be the amount of tasks. That can be also significantly less than the amount of tasks. And then at the synchronization step, we evaluate how are these n models with different weights per loss doing. And then we have a typical evolution step where we say the top contender we replicate. The middle ones are, from performance-wise, are surviving, and the bottom, the worst models, they are pruned away. And so like that, we basically consistently update the weighting of some of the models, and then lead to a really good weighting at the end.
Mm-hmm. And what are typical values of n? How far are we scaling multitask learning nowadays? What do you tend to see?
That really depends on the tasks or the application areas. It can definitely, in some cases, be, let's say, in the number of tasks or domains, like easily like 10 or more. But yeah, it's very dependent. In some cases, it's only a few, and then, of course, it's an easier problem.
Awesome. What's the next paper that you wanted to talk about?
I think the next paper to talk about is called EDGI. That stands for Equivariant Diffusion for Planning with Embodied Agents.
Okay.
And that one basically builds on a very well-known paper called Diffusers that basically uses diffusion models for a sequence of state and actions. And from that paper, the key idea was that you basically learn one model on states and actions, and then at test time, you can use kind of any reward functions to kind of perform your actions.
Mm-hmm. And as the diffusion models have become very popular recently in the computer vision domain with image generation like Stable Diffusion and the like, has diffusion historically been applied to kind of these state models that you're describing, or is that a new approach here?
No, this is more a new trend, and I'm not a full expert in the field, but to my understanding, the diffuser paper, which I think came out roughly a year ago, was the first one. And then what our paper from my colleagues are doing, the EDGI paper, they basically take this approach, but then they add equivariance to it. So like the problem is like in many of these systems, there's a lot of equivariances. So for example, if you think about a robotic arm, then like often the state space where they are is like a lot of redundancies, and we can like make this way more data efficient if we encode these equivariances into the algorithm.
Yeah, I imagine this this idea of equivariance and applying this technique is, I think, similar to the next paper we'll be talking about, which is geometric algebra transformers. It's how do we take the geometry of that's kind of inherent in these problems and use it to our advantage, as opposed to approaches that aren't geometrically aware. And it's something that's been a big focus for your colleagues like Johan and Taco, I see are authors on this paper. They've been working
Yeah,
on this for a
exactly.
while.
They work already quite a while on the topics of equivariance and how to be data efficient. And yeah.
And so the geometric algebra transformers paper is taking this similar approach, but to transformers.
Exactly. Like this sort of like takes it one step further. So the edgy paper is specifically to the diffusion models, and geometric algebra transformer is more general and combines kind of three concepts. So it kind of combines the concept of geometric algebra with like equivariance, and they use there like the equivariance E3, so that includes like rotation and translation variance in 3D, which is fairly general. Like a lot of prior art in that field is using often O3, which is only the rotation equivariance, but not the translation equivariance. And then the third component it adds to it adds a transformer-based architecture, which of course we all know that transformers are very strong in performance on a lot of different tasks, and that's really like kind of putting these three things together.
And is it putting them together in a very general way, meaning applicable to general tasks, or is it targeting a specific use case, or is it theoretical results? Like, what are the specific results that the paper is going after?
Now it's a very like generic approach. So it applies to anything where we kind of have representations that are have these type of equivariances. So, for example, it cannot be easily applied to, let's say, dense inputs, but that's also not the goal. But it really can like work where these geometric algebra are. So they use there the Clifford algebra, and where this is applicable. So that can be for regular numbers, point clouds, meshes, and all these type of data. It's easily applicable. So in these cases, for all these cases, it's working. And also in the paper, they show the performance on three reasonably different tasks, and like the robotic motion planning, which was the same task which they used in the edgy paper, but also they used like some really big meshes, where the meshes have like 7,000 nodes, and showed that it can scale up to significantly big data. So in general, also the two main selling points really is that it both has like strong performance, task performance, but it also has a really good scalability, and that's really one of the problems of many of these equivariance literature, that they often don't scale too well to really big data. So for example, many approaches would fail on these artery walls shear stress tasks. That's one of the mesh tasks they use, which have 7,000 nodes, and so that scales nicely to it.
And is it the incorporation of the transformers that lends the scalability in particular?
Yeah, it is the transformer, and also that it has, to my understanding, something which is fairly similar to linear attention. So in that sense, that gives it good scalability.
Okay. Awesome. We've managed to go into this conversation quite a bit without talking about LLMs, but I think the next paper kind of brings us there.
Yeah, definitely brings us there. Though we touched it slightly in the very first paper, and that's part on LLMs, but indeed, like the next paper is basically, it's a work by my colleagues on the LLM team, and they've collaborated there also with some folks from the UC San Diego. And it's about deductive verification of chain of thought reasoning. Maybe a little bit on the background. We know that LLMs, they're really good on many tasks, but for complex reasoning is still difficult. Like for example, like arithmetic or symbolic reasoning. And about a year ago, there came a paper out called Chain of Thought Prompting that was last year from Google. And basically, it means that the input question is followed by a series of intermediate natural reasoning steps, and that will bring us then to the final answer. And you can think of it like breaking down a complicated task into something which is a bit more bite-sized steps. And this chain of thought reasoning, that's sort of what was done before. And what people noted, I think that's not only us or my co-authors, but also others, is that there are still, like in LLMs, there's a lot of hallucination, and also in chain of thought reasoning that can lead to accumulated errors, which kind of limits the ability of the reasoning. And then what we see, if we look at humans, we have like very good deductive logic reasoning process, and we come to something very trustworthy, and we can also self-verify. And this is kind of something which they want to bring into the chain of thought. Basically a verification process, and they want to use the same LLM to do the verification, that it can be automated.
Meaning, so the LLM is performing the verification of the chain of thought reasoning process?
Exactly. And in order to do that, they introduce what they call a natural program. And then basically they do deductive verification steps in that natural program where they verify every reasoning step. So kind of like that natural program decomposes the long reasoning chain into like a series of reasoning steps, and then every of these steps is self-verified by the LLM.
Mm-hmm. And so the result is, are they going for, some kind of characterization or quantification of chain of thought reasoning prompts? Like, are they trying to verify them theoretically, or is it trying to provide the user with some indication as to the degree of optimization of a particular prompt or approach? Like, what is the specific thing that they're trying to enable?
So they're trying to enable that the output of the chain of thought prompting is better. So it's not like giving some extra output to the user, but it's really trying to get a more trustworthy output and improve the accuracy of chain of thought reasoning.
Got it. So as a user, I provide a chain of thought prompt, and the idea is that the model could do multiple things with that. This is going to tell the model kind of which is the best approach or which is the best way to structure that chain of thought.
Yeah, exactly. So it's kind of breaking it down, the problem, and then it does the verification steps in the chain of thought reasoning.
Oh, very cool. This year, as often the case, there were a number of demos at the Qualcomm booth as well. Can you talk us through the demos that you showed off this year?
Yes, certainly. So actually, like this year also, their NeurIPS also always have their own demo track. And actually we had Qualcomm had 4 accepted technology demos, and out of in total 15 demos. So we were very happy about that one. And we showed them, of course, also in our booths next to the official demo session on Sunday.
Okay.
And I think there's one kind of key concepts between all of these 4 demos, and that's really the focus area of on-device AI. Because on-device AI that provides a lot of benefits, for example, in terms of costs, energy, performance, privacy, and personalization. And almost all of these demos, they're also achieved by really full stack AI optimization. So what I mean with that is basically we have 4 levels of optimizations, from the systems optimizations, which can, for example, in language models, be training draft models or model or task optimizations, to more the model efficiency stage, where we do like things like quantization, knowledge distillation, pruning, what we talked earlier about. But then we also go to the lower levels, like the compilation, which goes through the Qualcomm AI engine and optimizes the performance there, all the way to kind of the hardware accelerations, where then these models run on Qualcomm's Hexagon NPU.
And I've done some interviews on and around this idea of full stack optimization, and we'll include a link or two in the show notes page so folks can dig into that in more detail.
Yeah, cool. Sounds good. Yeah, so and in total we have like 4 demos. The first one is on stable diffusion, where we show the world's fastest diffusion model in under 1 second. It runs actually in around like 550 milliseconds. And then we have one on as a fast AI assistance, where we showcase actually a recent Llama 7 billion model running entirely on the smartphone without any internet connections. And then we also have a demo on-device learning for video segmentation and on generative relighting.
Nice. Now, if I'm remembering correctly, earlier in the year, Qualcomm released some news or a demo about stable diffusion on mobile devices, and the speed has come down significantly since that initial attempt.
Yeah, that's true, certainly. Yeah, if I recall correctly, we had the first demo of stable diffusion where we used the original model at Mobile World Congress in February, if I recall correctly, and we were around, don't quote me, but 12 to 15 seconds, something like that.
That's kind of what I remember as well.
Exactly. But now we significantly improved that. And that comes really from the full stack. One is we actually show also a similar demo with the original model, which was around, I think, 5 to 6 seconds now. So that really comes from the lower stack optimizations. But also what's actually more interesting about this demo, where we show it in under 1 second, is that we used something we call multi-stage knowledge distillation. And there we basically perform 3 things to significantly improve the speed of the stable diffusion. One is we introduce an efficient UNet. So that means we reduce the amount of compute and the model size, and we do that by pruning away certain attention blocks, specifically in the first layer of the unit, which is at the most fine-grained, at the highest level of the feature map, and that's a lot of compute. But we found out they are less important, and we can prune them away and then regain the performance using knowledge distillation. So that's the first innovation to speed it up. The second innovation is based on guidance conditioning. So normally in diffusion models for image generation, we need to do the conditional and unconditional generation. So we need to run the unit for every diffusion step twice. And we here do guidance distillation, which then allows us to directly predict what is the output of the guidance instead of doing the conditional and unconditional model. And then the third and last step to optimize that is step distillation. So usually like stable diffusion runs with 50, or for example in our prior demo we run it with 20 steps, which gives us a really good outputs. But then we use knowledge distillation in order to train the model to predict more than just one step. So we basically try to predict multiple steps, and that allows us then to reduce the amount of steps in the diffusion process from 20 to actually only 6 steps. And like kind of these 3 innovations together with and then like that trained end-to-end is what allows us to bring it down to under 1 second.
That's awesome. That's awesome. I've asked this question in the past when talking about this full stack idea and optimization more broadly, but how generalizable, are those 3 steps? Like, do you see us evolving to kind of a process that you can throw a model in and apply kind of 3 steps or a catalog of steps and get an optimized model out? Or are we still kind of hand tuning and manually applying these approaches to get these kinds of results? Has that changed at all over the past year?
Really good question. And yeah, this is sort of where the full stack kind of comes in, is like, and really that what the part I talked about is the least generalizable, because it's very dependent on the task you're solving and the model. So I would say, unfortunately, this is not something you can put into a toolkit. We can put all the tools you need to do that in a toolkit, but you can't like have a one-click solution to optimize your model there, unfortunately. Of course, there were other models, as I mentioned, like, for example, the demo we had earlier in 12 or 15 seconds is now running in 5 to 6 seconds. So that are more the lower level optimization, and these ones are really, which everyone can benefit out of the box because they are on the lower level of this full stack optimization.
Okay. In the demos, the demos are talking about Stable Diffusion, Llama 2. Talk a little bit about the work that your team is doing around generative AI technologies as they've become so popular.
So yeah, I mean, our team is like doing a lot of different work. So on one hand, we're doing the studies which leads to the papers we talked earlier about. And also, of course, now with generative AI, like things become significantly more expensive. So for example, doing quantization aware training. So one thing we did in order to actually make the Llama model efficient on device, and we had to quantize it very aggressively. So it was quantized to 4 bits. And if you quantize it to 4 bits, it sometimes can lead to a small performance drop, or sometimes bigger. And in order, and so we were, for example, in the demo not fully satisfied with the performance of the post-training quantization model. So what my colleagues and us did is basically we did quantization-aware training and also combined that with knowledge distillation in order that the quantized 4-bit model has like as good performance as possible and is very close to the floating point model. And that is sort of the model we demoed. But of course, like, we know all like training LLMs is extremely expensive, and doing quantization-aware training is also expensive. Of course, it's only a fraction of the time of the original pre-training you need to do for quantization-aware training, but it's still, extremely expensive. And one of the teams of the works we are currently working on is we are looking at how can we actually make this more efficient, such that more parameter efficient as well as like more compute efficient.
Okay. Awesome. Well, Markus, we covered a lot of ground. Thanks so much for taking the time to walk us through Qualcomm's recent research at NeurIPS.
Yeah, it was great. Thanks a lot for having me, Sam.